is a video for preliminary engineering studies or Year 11 engineering studies for the HSC. And in this video, I'm going to be going through Chapter 3 of Year 11, which is braking systems, and we're in Part 3, which is materials. To start off, we're going to be looking at ferrous metals. I'm going to be following on with Engineering Studies, the Definitive Guide, and we have some stuff on steels. Now, that stuff I have already covered in other videos. So these are those other videos here, including my video, including a reference to maybe the astonishing panorama of the end times. There's a it's a good Dragon Ball video where they transform, and it's a bit like White Heart steel transforming. Anyway, I'm just going to play it quietly in the background, so while I'm working. Okay, so we're going to quickly review ferrous metals, very, 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 very quickly. Okay, so what we know is that steel is an allotrope, which means it can form more than one. Steel is polymorphous, which means it can have more than one crystal structure. So what are those crystal structures? It can be FCC or BCC, or we're going to learn later, it can also be body-centered tetragonal, which is a BCT. Okay, so there's some different phases. We have austenite, ferrite, cementite, pearlite, and we're going to just do a quick recap on that, where we've talked about that in Chapter 2. I covered that in Chapter 2 materials in landscaping products, and I'm going to quickly go through that again here. So what I have is, we don't need that window anymore. Okay, so here's the phase diagram for steel in the region that we're interested in. Now, steel has actually got a really big phase diagram, this thing here, but so we're not really interested in the liquid range. We're interested in this range here, but these areas here where it makes a V shape, they're called eutectoids, and eutectoids come from the Greek word for happy melting. The idea is that this is the temperature where we can most easily get liquid steel at about 4.2% carbon. And this is why cast iron tends to have a higher carbon content, because it melts more easily. We have a phase diagram here, which does a good job of showing that as well. So at this temperature, it's liquid. And then as it starts to cool, so this is one eutectoid, and then we're more interested in this range here with this eutectoid. At this temperature, what we get is 100% austenite. Down here, we'll start to get austenite and cementite. Here, we'll get pearlite and cementite. Whereas on this side, we'll get austenite and some ferrite, and then eventually the austenite will transform into pearlite, and we'll have some ferrite there as well. The point where we get the eutectoid point is where we're going to get 100% pearlite. Now, what is pearlite? We've mentioned before that pearlite is a combination of alpha and ferrite and cementite, alpha and Fe3C. So here we have ferrite. The ferrite is a body-centered cubic, right? Hence why it's got a good body. And cementite is also known as iron carbide. Now, we get the eutectoid point for pearlite, where we get 100% pearlite, where it's going to transform into, without going through two phases, is at 0.83% carbon. So what do we got now? What are we going to know next? So we've just quickly described austenite is FCC, right? And it's ductile. Somewhere out along here I have a picture where we're standing behind a whole bunch of ducts. But the point is, we remember it's face-centered cubic, so we've got a picture of his face. And ferrite is a body-centered cubic. I got another. If you go back to my notes, there we go. See, it's ductile with all the ducts. It's not very clear. There's some ducks, and the ducks are wearing sunglasses. Okay. Okay, pearlite looks a bit like stripy, like a zebra. So we've got that covered. Now, the thing that I want to talk about, I've just described what eutectoid means. Some books simply say 0.8. That's fine. Eutectoid is this point where we see this V. And we can refer to things as being hypo or hypereutectoid. And how I like to remember that is I like to, somewhere here I have a picture that is saved. I have over. It should be here. Here we go. So do you see how this shape here makes a V? I like to write the word over on the V. And what do I get? I get O for hypo. Hypothermia is when you have not enough heat. If you're out in the cold, you're going to have hypothermia, not enough thermos. Yeah. If you're hyperactive, you've got too much sugar. Actually, sugar has nothing to do with behavior according to controlled studies. But if you're hyperactive, it means you've got too much activity. Yeah. So hyper and hypo. So you can have So that's the terminology. Hypo means under. Now you might hear diabetics. They can be hypoglycemic. That means they don't have enough sugar. And if they don't have enough sugar, well, they faint. Whereas hyperactive kids who have had too much sugar, well, they've got too much energy. So hyper and hypo are different. So we call this side is the hypoeutectoid, and this side is the hypereutectoid. Okay, so we're done with that. Okay. So we talked about the phase diagram. We talked about how I have a whole, I have a worksheet and 2 videos talking about the content on ferrous metals. We've talked about phase diagram. We've talked about hyper and hypoeutectoid. It's worth also talking about quenching katanas. Oh, I don't need this diagram anymore. That was from the previous video. I can save that. Okay, so we're done with this one. Okay, katanas, not Kitana from Mortal Kombat, different person, different thing. Kitana spelled with an I. Okay, differential heat treatment is when we quench, when the Japanese, when they made katanas, they didn't temper steel. Instead, what they did is the way they quenched the steel is their swords, that they would take a straight sword and then they would coat it in clay on the outside. And then when they quenched the sword, what would happen is that the sword would actually bend backwards. And that was because only the tip would become hard and the inside would stay soft. And this would mean that it would still keep a very sharp edge so it could slice through things, but it wouldn't snap if it hit armor or another sword. And we can see it leaves a pattern on the blade where you can see the side that's been hardened compared to the side that hasn't. So that I thought was worthwhile. I'll just show you that. So you see how the sword goes from being reverse bending. I'll just show you that one again. Goes from being reverse bending. So it starts off straight, reverse bending, and then it straightens in the direction that we think of as when we talk about samurai swords. Okay, so well, the next thing we're going to talk about is testing. So we should have testing. Now, when we talk about testing, I've got this picture here of this guy, Sam Rockwell. He played the hammer in Iron Man 2, and he was a baddie. And when we go to, we've already seen the tensile test. We're now going to look at the next test is we're going to look at is going to be compressive tests. Okay. That was the same window. We're just going to click on it through here. So what we can do is we can do tests on concrete to see whether or not the concrete is very good. You know, actually, before I get started on that, I should have a concrete mixer somewhere. Great. Okay, so that's what we're up to. So this is a concrete. These are concrete mixers. When I built my house, I mixed the concrete in a concrete mixer like this. But generally, if you're building a normal house, you would order concrete and come on the back of a truck, something like this. And you might be familiar with the Cobra Kai scene where they're in the concrete mixer. You don't want to do that. That would be a bad idea. Concrete it's not acidic. It's the opposite of acidic, but it's still going to hurt your eyes. It's basic. And it certainly, there's like small bits of sand in there as well. It definitely would be a bad idea. You could easily blind yourself doing that. I don't suppose they needed to have a warning, don't try this at home. Most people don't have access to a cement mixer to do that anyway. But let's say that we're going to imagine that I run a concrete plant and I want to send concrete to my brother Bob, and he's building a house. And then along the way, George, he's the guy who drives the concrete mixer. George, he gets stuck in traffic. And he's really worried because he does not want to have to chip concrete out of the back of a concrete truck, right? Just like the kids in Cobra Kai. So what he does is he says, you know what, instead of getting a bunch of kids to spin the concrete mixer, I'm just going to pour some water into the concrete mixer. What's the problem with pouring water into the concrete mixer? It dilutes it, just like if you watered down iced tea or a drink like that. So yeah, it means that the concrete's not going to be as strong anymore. And so this could be a real disaster. So so that we can actually buildings collapse kind of disaster, catastrophic failure. So to make sure that that doesn't happen, what we do is we test. We get concrete cylinders. We cast concrete cylinders before we, when George pulls up on site, I pour some concrete into a cylinder and I test them. We're going to talk about curing in a second. Okay, so what those cylinders look like is they look a bit like this. And we test them. They've removed the grate and they put acrylic here to protect the camera. And you see it explode. Now, typically, if you have to answer a question, say, how does concrete cylinders samples break? I skipped some stuff. I really should look before I keep going. I'm going to finish off the stuff about concrete and then I'm going to go back. Okay, it will typically fail in what we call here hourglass fracture. And that's what you should draw in an exam. And there was, in 2020, there was a question asking about how does concrete typically fail under compression. Hourglass fracture is what you want to write. Okay, I'm going to quickly go back and just talk a little bit more about steel. I felt as I'd skipped too fast, but, is what it is. Okay, so here we have just quickly as we get closer to perlite, we can see that our strength keeps on increasing, but strength actually goes down once we go to 0.08. Why would we ever want to have a higher carbon steel? Because what we want is hardness. So for things like drill bits, we want to have high hardness. And we're going to learn about how we measure hardness in a second. Toughness goes down as we go, as we get more and more perlite. That's okay. That makes sense. Okay, so that's that covered. Just quickly, when we quench steel, we make a BCT, a body-centered tetragonal. It looks something like this. It looks like a stretched out body-centered cubic. And if you have to draw the diagram, just draw a whole bunch of lines like this and then label it acicular martensite. Or if you wrote needle-like martensite, I'll give you that as well. Okay, we've got different uses. So we've said dead mild is for structural steel. RSJs are what we used to use instead of universal beams and universal columns. They have an I-beam shape, except they're tapered. And we can see that for medium carbon steel, where we have things like axles, crane hooks, 0.6 is what we use for rail. And then for 0.8, we have things like cold chisels, punches. And then for very high things, we have saws and razor blades, knives, that sort of stuff. So things that need to be very hard. If you see down the bottom here, I actually have a link to a study from MIT talking about why razor blades chip, even though they're so hard and they're cutting something that's much softer than razor blades. And that's because of very, very tiny cracks, is the answer. Okay. We should talk about curing. Yeah, testing concrete, compressive test, Curing concrete. Okay, concrete cylinders curing concrete. Okay, so I've got a song by The Cure, but I like mariachi music, so it's in mariachi style. Why do we cure concrete? Well, we cure concrete to make it strong. How do we cure concrete? Well, what we do is when it's cast, after we cast concrete, we spray it with a hose or something like that, and we can cover it. That's another way of curing it, to keep the water in so that the chemical reaction can take place. It doesn't evaporate, right? We actually we want to make sure that there's enough water, not that it loses water. You can do both. You can cover it and say Hessian and then wet the Hessian. That's a good strategy as well. But for the samples that we saw before, we actually keep those samples in water. So we keep them in like a bath. I should have a picture of that, but just in case I don't. This is another example. So someone's got a sprinkler, and curing is really important to strength. So let's have a look. If we look at this picture here, so we talk about concrete getting stronger. So first of all, within 7 days, we might have got to about half our strength. And what will happen is that after George shows up at the site with his concrete truck, we will check it after day 1, and we'll check it after day 3, and we'll check it after day 7. And if we see there's a problem, we want to jackhammer that concrete out as quickly as possible, because it's only going to get stronger. The longer we leave it, the more difficult it's going to be. Generally, it has to pass the strength test by 28 days. Now, we do say that concrete actually gets stronger and stronger forever, even though here it's showing as going down. So the difference in strength for the same material, we can see that if we just dry it in air, we're going to get 30 megapascals, whereas if we continue to cure it, we can keep on getting way up above 50. So we can get a lot more strength if we cure. If we cure for 28 days, we'll get 45. If we cure for just 7 days, we get 5 or maybe more megapascals less. So it's pretty important. I had another picture. Oh yeah, so this is just with Hessian and water on top of it. Okay, so here we go. So what they do is they write the day that the sample was taken, and then they just write a number on the cylinder so that they can say this was test piece 12, this is test piece 150, so they can tell which test piece was which. Okay, so we talked about compressive tests. Let's check that hopefully we've already seen this one. That's that one there. Good. Okay, so now we're up to hardness, and most people are familiar with the Mohs hardness scale, and they're aware that diamond is the hardest and that there are some other ones in between. Now, we don't, as engineers, don't usually use this scale, right? It's not specific enough for us, but it's worth just as a general rule saying that a knife might be 5.5 and a nail might be 6, whereas regular glass is 5, where Gorilla Glass might be 6. And that's why Gorilla Glass scratches the knife, not the other way around. Okay, so this is a Rockwell hardness tester. We saw a picture of Sam Rockwell earlier, and we have one of these at school. These are pretty common. They're used because they're fairly accessible, they're fairly quick. That's their big advantage. To help you remember, I've got the picture of Sam Rockwell. Sam Rockwell's been in a lot of things. I liked him in Moon. He was in Jojo Rabbit. That's him in Jojo Rabbit. He played George W. Bush. He was in some other things. That's Moon. Can't see the Ninja Turtles picture anymore. That's a shame. He was also in Ninja Turtles. There we go. That was him in Ninja Turtles. He did an AMA on Reddit, and I asked him about hardness. He did not answer my question, and I was very disappointed. Okay, so what's the difference between the Brunel hardness test and the Rockwell hardness test? I mean, well, I may have jumped a step there. You may not even be familiar. There is a Brunel hardness test. Let's have a look. Are we going to go back down to testing? I'm not interested in this stuff. And we're at testing. Okay, so we've got Brunel, and we've got Vickers, and we've got Rockwell and Shaw. So we'll start with Brunel because Brunel is the oldest. It comes from the before time, and it uses a ball, and we use it where we're using where we have big grains. And the disadvantage of it is that it leaves a big mark. It's bad because it leaves a big mark. We might call it destructive testing. So that's the first one. And then we have here Rockwell Testing. Testing looks almost exactly the same. What's the difference between the two of them? Well, we use Rockwell. It doesn't leave a big mark, so we can use it on a finished test piece because it doesn't leave a big circle mark. It's a much less conspicuous test. Oh, Sharpie test. I'm going to take a photo of that. Okay, so why do we use it? Well, they use different kinds of impact, and this one talks about the different advantages. So it says, like here for Brunel, Brunel is used for coarse or inhomogeneous grain structure, used for larger samples, so big samples. It's a ball. It's from the before time, the Brunel test. It's bad because it leaves a permanent mark. The Rockwell test we use because it's mainly pretty quick. Can be used advanced tests. Okay, so that's where they're used and why they're used. What's the difference? Well, so Vickers uses a square pyramid. Brunel, we said, uses a ball or a sphere, and Rockwell uses a cone. So that kind of helps you to understand what's going on with the different testing. Now, what is the comparison between these? Let's have a look at, so that's a Rockwell tester. We saw that, the next one we talk about is the Vickers test. So this is a clip from District 9, and District 9 is, I guess, a pretty, it's a metaphor about conditions in South Africa, and there's a character called Vickers. His name's actually spelled, I think, W-U-K-I-S or something like that, but for our purposes, we're going to pretend it's Vickers. And he is trying to get this alien to move out of his home by giving him cat food because they really like cat food. And I'll just quickly put that scene on. We probably don't need any more cure.
Because you know this. Well, this is a nice cat food, you know. But of course, it's not your house, eh? So we'll just have to go and we need you to sign there. Okay, there it is. Now you can take that. All right.
The creatures became incredibly obsessed with cat food. There's something about that. It was like catnip for cats, only a lot more intense.
Okay, so how I like to remember this is that the Vickers test is good for thin metals. Thin metals. The thin metals like for a cat food tin. So if you need to use a cat food tin, you've got the thin metals, you want to use the Vickers test. Whereas the Brunel is good for big metals and with big crystals. Rockwell we use because it's fast or it's relatively quick. And the last one we're going to talk about, the last hardness test, is the Shaw. Okay, so this is a conversion table. So it compares Vickers to various Rockwell hardnesses. So various Rockwell hardnesses, various Brunel hardnesses, and here we have Shaw hardnesses here. And the Shaw hardness tester, well, you can see here, this is a Shaw A durometer. So there's different kinds of hardness tests, but this is Shaw A, and it's just measuring some material. Oh, why do we like Shaw? Because it's portable. You can take it on site much more easily. Where so this is a guy making BJB. Is that the same person? No. He's making chocolate that's harder than steel. And I had a student ask, how is that possible that the chocolate could be harder than steel? So this is a Shaw D test. So that is where I got this link for Shaw D. Okay, so this chocolate is reading on the Shaw D hardness test 94.5, which, even though there's a 0 there, it looks like it's actually pretty close to the maximum for the scale. Shaw D, well, this one here doesn't even go up past 6. Let's have a look. So that's Shaw D. Yep, that's the chocolate test. Oh yeah, okay. And then here. Okay, so here we've got Shaw D hardness test of 98, gives us a Rockwell hardness of 58, right? That's Rockwell hardness C. And what does that relate to? Well, if we go to this one here, Okay, so 58, it gets us down into this area here. So it's harder than steel, but not as hard as the cutting tools. So that gives you a rough idea of how hard that chocolate is. So the idea as well, we can compare. So diamond is way up here on the Brunel test, and then gypsum is way down here on the Brunel test. This is logarithmic, so like diamond is a lot stronger. Like if we see here, diamond is 5 times harder than the next step down. So this is, we could say that topaz is twice as strong as, sapphire is twice as hard as topaz, and then diamond is 5 times harder than that again. So if we don't have the Vickers test here to show relatively, but these are pretty linear actually until we get to diamond, where it just shoots way up. Okay. That I think is pretty close to it for materials. Yep, they're just showing a Rockwell hardness tester. They're showing a tensometer. We've already looked at tensometers. It's not quite done. I did skip through this part. I'll quickly go here. Okay, so after we talked about different kinds of metals, I skipped through. I haven't gone exactly in order, so I apologize for that. We've got composite materials. We've already talked a little bit about composite materials. They've got their own page, and I've talked about them in the first video on materials. But we're familiar with timber being all wood is a polymer. It's a polymer of cellulose, which is the monomer is glucose, and it's held in a lignin resin, and that's also a polymer. But then in next year, when we do volume 2 in the Year 12 book, chapter 1, we're going to learn about engineered timbers, things like plywood, LVL, and glulam, and we use those when we want timber that is larger than we can provide. So for instance, we can't really grow a tree big enough to make a flat wooden board, and these days big trees are pretty scarce or protected, and at this point it's pretty hard to get. You can't go and buy 8 inches of oak anymore. So what you have to do instead is you have to use smaller pieces of weaker timber, and they're stronger because of the glue. So we can have LVL, which is made of thin veneers, which is like plywood but a beam, or we could have glulam, which is like just wooden beams glued together. They also are less likely to have defects, so that makes them stronger. They can be designed into for any length and any shape. Compared to steel, they're easier to cut and join. Okay, so that's timber. Asbestos, we talked about asbestos and how it was banned. We talked about how it's a combination of, for our purposes, what it was replaced with is polyamides like Kevlar and nylon, and held in a binder of phenylformaldehyde. But we've talked about how asbestos was used as in fibers. We also in fibro as well, worth mentioning, beyond the scope of brakes. We have sintered metals. Sintered metals is what I wanted to talk about. So sintered metal composites, also known as powdered metallurgy, is where we make things out of powdered metals, I guess is the short version of that. We will cover this again next year, but I'll just quickly use the example here to talk about if we want to make a metal brake pad, well, we don't cast it. Rather than casting it or forging it, what we'll do is we'll take different metals and we'll grind it up into very small amounts, and then we'll fuse it together under heat. Now we'll look at examples of that later, but for the moment what we're going to say is that powder metallurgy has the advantage that it can make very complex shapes, and that it can also help us to join materials that don't alloy well. But the downside is that it's often not very strong. It doesn't have very good tensile strength. So this can be good for things like Happy Meal toys. If you have a Happy Meal toy, so it might have metal components like gears, but those gears are not going to be cast and machined. No one has time to cast and machine a gear that's going to go into a toy that's going to cost 30 cents total. So instead they might use powder metallurgy, because then that gear is going to be ready to go straight away without any additional machining. And yes, it won't be as strong as it might be if it was made out of a cast and machine material or a forged material, but but it will be strong enough for the Happy Meal toy. Whereas a car is exposed to much higher loads when it hits a pothole or something like that. Okay, yeah, so like we said here, sintered metals can be fused together with phenyl formaldehyde resins. Very good heat dissipation. We've already talked about metal brakes as above, and yeah, so they can use Kevlar, which we said is polyamide, and alumina as part of as a composite material. Okay, how do we make brake linings? Yeah, I don't think I really have anything that I can add aside from just reading that section. We've said that the phenyl formaldehyde is the resin that holds things. That's a thermosetting polymer, and that the fibers are often polyamides. Yeah, I don't think I can really add anything else. We've looked at these pictures here earlier, and we've talked about, so which one of these has the highest strength? Well, that's going to be top left. Which of these is the toughest? Yeah, B or D. So one of these two on the right. So which ones? There's two that are very ductile. Which two are very ductile? Yeah, the two on the bottom, C and D, are very ductile. This one here has some plasticity, whereas this one we'd call brittle because it's a stiff material. They're all pretty stiff materials, but then this one is brittle because it doesn't have any plastic deformation at all, and very stiff. This has lower strength. How we can measure strength is its height on the vertical axis. Okay, and we're back to concrete. So we bounced around a little bit there. I apologize for that, but we've now covered all of materials for Chapter 3. I still have to talk about engineering reports and communication, so graphical communication, but that will do for Chapter 3 today.